Okay, so continuing with quantitative. Just real quick, defining structural, I don't know why I'm in red, structural formula. This shows the arrangement of the atoms and bonds in the molecule. Okay, isomers. Isomers are two compounds with the same molecular formula. Okay, but different arrangement of those atoms, or different structural arrangement. Okay, structural isomers. Okay, so those are things that have different structures, same formula. These are going to have sometimes very different chemical and physical properties. Okay. Okay, so chemical, and this should be pretty straightforward. So chemical equations, okay, and by extension chemical reactions. We form new substances. Bonds are broken, which always requires energy, always. Okay, and then bonds are formed to make new products. That should be bonds. Okay, and this always releases energy when new bonds are formed. Okay, so always this will result in some kind of energy change between the reacting system and the surroundings. Okay. From the balanced chemical equation, you have a fixed relationship between number of particles of reactants and products. And remember, that has to be a mole basis. Okay, you have to define those by a balanced chemical reaction, or chemical equation, chemical equation. Don't forget state symbols. If they require them and you don't have them, you lose points. If they don't require them and they're wrong, you don't lose points. So, okay, sometimes you will have to identify the spectator ions, and these are the ions that would be the same before and after the reaction. Okay. Solutions, and we're going to do some more problems in class. Okay, solutions. Remember, molarity, capital M in the US, typically written moles per decimeter cubed, or moles decimeter -3. Remember that a decimeter cubed is the same thing as 1 liter. All right, and you can write it as this, and that means molarity, moles per liter, as a concentration. Volume times the molarity is going to give me the moles of the solute. Okay, because basically you will have some liters, X amount of liters, times your Y moles per liter, which is your concentration and molarity, hopefully you can see that'll give you moles of solute. All right, so remember gases. Ideal gas, PV equals nRT. T in Kelvin. Okay, R that I remember is a 0.0821 liter atmospheres mole Kelvin. 760 millimeters mercury is equal to 1 atmosphere. That's equal to 101.5 kilopascals. Ideal behavior occurs at high temperature. Okay, so the intermolecular forces are way outweighed by the kinetic energy and low pressure. So high temperature, low pressure. Molar volume at 22.4 liters for 1 mole is only for gases, and this is only at standard temperature and pressure, which is 273 Kelvin and 1 atmosphere. We're going to do, I think, some problems on limiting reactant, yield, percent yield, and excess reactant, and it's usually the excess is what throws kids off. We are going to be doing an acid-base titration. Okay, wouldn't hurt to look up some of those things. Okay, glassware. All right, beakers for measuring volume, very inaccurate. Okay, because it's plus or minus about 5 milliliters, 5 centimeters cubed. Better is a graduated cylinder. Okay, but it's actually still considered quite inaccurate. Okay, plus or minus about 1 centimeter cubed. A burette is more accurate, considered accurate, because it's plus minus 0.05 centimeters cubed. The pipette is also considered accurate. But the thing that you have to remember with these two is how many multiple measurements. And every time you add a multiple measurement, you are increasing the uncertainty. Okay, volumetric flask is considered accurate to plus minus 0.05 centimeters cubed as well. Okay. All right, so there are some example problems we have to do, and I might set them up as separate screencasts.